In this lecture, we are going to talk about Galois theory of separable isogeny. So say we are given a separable isogeny phi. So this isogeny phi takes elliptic curve E1 to E2. And we have seen in the previous lecture that this isogeny or rational map will introduce this field extension, which by definition is equal to degree of phi. And in the previous lectures on elliptic curves, we have shown that degree of phi is precisely equal to the order of kernel of phi. So here in this proposition we are showing that if you have a separable isogeny like this, then we have a Galois extension. So this extension is Galois. So extension being Galois means that this is equal to the size of this extension, or dimension of this extension is precisely equal to the order of our Galois group here. So this is the Galois group, and since this is equal to kernel of phi, so this kernel of phi comes right here. You have an equality here, so this gets here. So kernel of phi is isomorphic to the Galois group of our field extension, which you get from our separable isogeny. So we want to prove this big result. So to do this, first we'll prove a simpler result, that this phi is unramified. So that is, we want to show for all points P on elliptic curve 2, phi inverse of P is precisely n, where n is nothing but degree of our isogeny. So for this we will use a small fact that there actually exists a point T on elliptic curve E2 with n pre-images if degree of phi is n. So there does exist such a point for an isogeny. So say this T has n pre-images, q1, q2 all the way to qn. So we are going to use this fact. Now if P is any arbitrary point, it will also have n pre-images. So we have to show that for all points P in E2 there are n pre-images, and we are using a fact that there is at least one point which will have n pre-images. So you pick up this arbitrary point P in E2 which has n pre-images, and say there's a point Q which gets mapped to P. So then the n pre-images are, say, just Q, then Q plus Q2 minus Q1, Q plus Q3 minus Q1, all the way to Q plus Qn minus Q1. So this Q we can actually rewrite it as Q plus Q1 minus Q1. So obviously once you apply map phi to it, the second portion will get vanished because Q2 and Q1 will get mapped to the same point T, which will cancel out. So only thing you are left with is Q. So you were able to take these n different pre-images, and out of those pre-images you were able to construct n different pre-images here. So again, once you apply map phi to it, you will get P, because both of these points will get mapped to T, which will cancel out. So now we want to prove this theorem. So first we talk about a translation map. So say we have given an elliptic curve E over K and given a point T on the elliptic curve. So corresponding to this we get a translation map tau of T, which takes point P on the elliptic curve and adds T to it. So P to P plus T. So this gives rise to our map tau star of T in algebraic geometry, which takes function field of elliptic curve to function field of elliptic curve. Now look here. So phi is unramified, so inverse image of a point, there are n points. So for kernel of phi, you can take inverse image of a special point and there will be n points like this, t1, t2 all the way to tn. So all these points are living in E1. Then this tau star of Ti, so this is translation map for each of these points, will act on Ke1 while preserving phi star of Ke2. So this is what we will show. So first thing you have to notice that phi star of f is f composed with phi. So this you can see in terms of algebraic geometry. So say we are given a map like this, C1 to C2. So corresponding to this map, we have a contravariance which goes like this, from KC2 to KC1. So there is a function f living here. So basically this function f, if it is acting on a set of points, those points are in C of 2. So we want to transfer this function here. So the way to do it is, if you have this map phi here, what you do is you first apply phi and then you apply f. So the function living here could be f composed with phi, because after you apply phi you come to the space C2 on which you can have function f, and corresponding to this you have phi star here. So you have phi star f. So basically we are pulling back the functions living on the space C2 to space C1 via phi, and that is precisely the definition here. So we are going to use this contravariance now here, so you can see this carefully. So this phi star corresponds to the homomorphism of rings. So this tau star ti phi star f. So now first contravariance, you keep this as such and use contravariance here. So you have phi star f, you have taken tau on this, you remove the star, just like here you remove the star of phi, it comes here. You remove this star, this tau ti comes here, but tau ti is just adding this point like this. So it is any point, arbitrary point, so any arbitrary point which we are denoting by dot plus ti. So this is the map. So now the star is there, again apply this contravariance. So just like the star is here, it comes here, so this will come in front of f. So it comes in front of f, it's point plus ti. So obviously this will become phi of point plus phi of ti, but this ti is in the kernel, as you can see, so you can just drop it because it's just you just add it to this point, you just get phi of dot or phi of our point. So this get f phi of dot. Now this f phi here is the same. Now you rewrite it as phi star of f. So notice that all these points are having no impact at all on our phi star of f. You put these points in there using translation map and it has no impact. So this phi star, when it acts on this here, any function f here, these points have no impact on it. So these points act through this on ke1, but they preserve phi star of ke2. They have absolutely no impact on phi star. As you can see here, you're putting these points but they are having no impact. So the number of automorphisms of this field which fix phi star of ke2 is greater or equal to n. So this n is precisely these points. So at least these points are having no impact on the automorphisms, because every time you put a point here, as we can see here, it has no impact. So this is at least n, but by definition you know this degree of extension is n. So now by Galois theory you know this is greater or equal to n, but degree of extension is n, and our Galois group is the group of automorphisms. So this is precisely this. So this is precisely, this thing is our Galois group. So this is our equal to the size of our Galois group. That is a group of automorphisms like this. So our Galois group, which is precisely here. So we are done with this theorem. So let us now see a quick application of this. So now we want to prove this theorem. So say we are given non-constant isogenies psi and phi with phi separable. Say phi goes from E1 to E2. So phi goes from E1 to E2 and psi goes from E1 to E3. So you have E1 to E2 and then you have E3. So this is our psi and this is our phi. And kernel of phi is contained within kernel of psi. So then there exists a unique isogeny lambda. So there is some isogeny which exists here lambda, so that this diagram commutes. So lambda goes from E2 to E3, and you can see you can first apply phi and then lambda is same as applying psi. So psi is same as applying first apply phi and then lambda. So the way we are going to use prove this theorem is that we are going to write the corresponding figure in algebraic geometry and say that there is a corresponding morphism here which will show that this holds. So corresponding to this phi we have phi star, corresponding to this psi we have psi star, and we will show that there is a mapping here, and this mapping, we are our big theorem of algebraic geometry, will induce this lambda because there is a one-to-one correspondence between this diagram and this diagram. So let us show this. So first see this field extension, so you're going from phi star ke3 is getting embedded into ke1. So this is the field extension. So phi star ke3, this is fixed by all the points in the kernel of psi. So as above means exactly here how we showed that all these points are fixing this, preserving this phi star ke2. Similarly this is preserving psi star ke3. But now notice this condition here. So say there are a bunch of points in kernel of psi, and this kernel of psi contains all the points in kernel of phi. But because we are saying phi is separable, this kernel of phi is precisely equal to the Galois group of our corresponding field extension here. So Galois group of this field extension due to this. So ke1 over phi star of ke2. So this is the Galois group. So notice that in Galois theory there is kind of a contravariance. So this the morphisms which fix phi star ke2, they are going to fix these points. So they are obviously going to fix the points of kernel of psi, because these points are contained within the kernel of psi. Obviously those morphisms might fix some more points, but they will at least fix these points here. So the points lying in kernel of psi are going to get fixed. So notice that there is some kind of contravariance in Galois theory, and therefore by Galois theory you have this psi star of ke3 lying within phi star of ke2, which lies within k bar of e1. So we have been able to construct this map right here we are using Galois theory, which is right here. So ke3 to ke2. So this you can write as psi star of ke3, this you can write as phi star of ke2. And this function field inclusion gives us the required rational map lambda, which goes from e2 to e3. So you can find all this on page 73-74 of Silverman's book Arithmetic of Elliptic Curves.